So this lesson is simplifying radicals, and I'm gonna autofocus that. So we are going to be able to, by the end of this, simplify radicals using a prime factorization of numbers and expressions. So the first thing that we need to look at, if you're following along with your guided notes, is the parts of a radical. So this number that's hiding in here inside of the radical is called our index. That tells us what root we are looking for. Of course, this is the radical itself, and the thing underneath the radical is called a radicand. Try to say that 10 times fast. So if this number isn't there, if it's not visible, if it just looks like that, then we are to assume that it's a square root so that our n value is actually 2. And my camera will catch up with us in a second. There we go. So we're going to go through some examples looking at what happens if our radical is a square root or our index is 2. So let's start with this example. I have the square root of 16x squared. So what I'm looking at is, what's the square root of 16? What's the square root of x squared? Well, I know that the square root of 16 is 4 because 16 is 4 times 4. And x squared is just x times x. So the square root of x squared is just x. So I could write that the square root of 16x squared is equal to 4x. This is a factor tree. Because these are perfect squares, I only broke it down this far. But what happens if it's not a perfect square? I am so glad you asked. I'm going to start working through my factor tree. So I can write this as 2 times 9. And I'm going to keep going. Now, yes, 9 is a perfect square. But just to clarify and make it extremely clear what we are doing, I'm going to break down 9 into its prime factors. Because this is a square root, I am looking at numbers that multiply together that are in a pair. Because it's square, it has to be 2. So, 3 times 3. This tells me that inside of this prime factorization, I have a group of 3's. So, I can show this 3 on the outside of the radical. What this is showing me is that I had a pair of 3's in that prime factorization of 18. And the only thing that was left over was 2. Now it is possible, if you have on your fancy pants, you could stop when you got to your perfect square of 9 and know that I have the square root of 9 multiplied by the square root of 2. I know the square root of 9 is 3. But this will not always work in our prime factorization. Or excuse me, this won't always work with some of the numbers that were given. Sometimes we're going to have to use prime factorization. So, let's do square root of 60. So, for my brain, the first thing I think of is this is 6 times 10. Neither of those are perfect squares. I have to keep going. I have to get down to my prime factorization here. So this is 3 times 2. So I'm done with 6. I've knocked that down to its prime factors. And this is 2 times 5. I've knocked 10 out because I've put it into its prime factors of 2 and 5. Personally, I cross the numbers out as I go so that I don't accidentally think that I need to include 10 when I go back to write my final result. So here I have a pair of 2s, so I know that these can be represented on the outside of my radical, showing that I could take this 2 times 2 out of my prime factorization. Because this is a square root, I have my pair, I have my group of 2. Now I have a 3 and a 5 left over that have to go inside. But it's not 35, it's 3 times 5. So ultimately, in the end, I have 2 radical 15, or 2 times the square root of 15. So next we've got 3 times the square root of 40. Well, I'm going to do 2 times 20, just to throw a wrench in. Sometimes all you can think of is that's something that can be divided by 2, and that's okay. But I am going to have to keep going because 20 is not prime. I can knock 20 down even further. Well, that's 2 times 10, and that's 2 times 5. Now I'm going to cross out 20 and I'm going to cross out 10 because I have factored them. They are no longer in play. Now I'm going to look for pairs of numbers that I could group together so that I can show I can take them outside of the radical and make them a coefficient now. Well, there's a pair of 2's right there, but I've got 2 times 5 left over. So I'm going to put 2 outside the radical to show that that pair existed. And then I have 2 times 5 inside of my radical. So, oh, excuse me. Don't forget, Miss Hall, there's a 3 that was already outside. So I have to multiply that 2 by the 3 that was already there in my original problem if I had taken a second to look back. So my final answer is 6 radical 10. So it always pays to take your time and not rush like I just did. All right, now I'm throwing variables into the mix. It does not change anything. I'm going to start with 24. I've got 2 times 12. I'm going to knock down 12 to 2 times 6. And I'm going to knock down 6 to 2 times 3. All the way down to 2 times 3, Miss Hall, 2 times 3. So I've knocked them down to prime factors. I've got a pair of 2's. Those are left over. So I know at least this far, I've got 2 times 3 inside of the radical and 2 on the outside because I had a pair of 2's so they could take a walk to the outside. Now for the x's, I've got x squared. I know that's x times x. That's a pair of x's right there. So they're going to go outside to show that this was a perfect square. I could take the square root of that. Boom, x. There we go. Y cubed is y times 1 more y. That's y multiplied by itself 3 times. I have 1 pair of y's and an extra y left over. There's my leftover guy. So I have 2x on the outside of my radical. I have a y on the outside of my radical because I had that pair. And then I have 6y on the inside. All right. I'm going to ask that you pause your video, try both of these problems without me, then unpause, come back and check and see how you did. So I broke down 32 into 4 times 8. Because we're thinking prime factorization, I'm going to keep going, even though I know if 4 is a perfect square. This is 2 times 4. And this is 2 times 2. I'm going to cross everybody out that's already been factored out. So I have 2 pairs of 2's with a 2 left over. So I'm going to put a 2 on the outside multiplied by another 2 on the outside. I'm going to leave some space and put a 2 inside. X to the 5th is 5 x's. 1, 2, 3, 4, 5. So that's 2 pairs of 2 x's and then 1 extra. So I have 2 x's that are going out front, which I can write as x squared, and then 1 lonely x going back in. Y to the 4th is 4 y's. So that's 2 pairs of y's. So I can write that outside as y squared. I'm going to simplify as much as I can. All I can do is write 2 times 2 is 4, and then everything else will stay the same. So that's my final answer there. For 45, I've got 9 times 5. 5 is a prime. I don't have to go any further there. So there's a pair of 3's. There is a 3 already out front. I'm not going to forget this time. So I have 3 times 3 on the outside and a 5 inside. I have 3 x's here. So 1 pair and 1 extra. The 5 was extra as well. This y, I don't have enough to make a pair, so that's staying inside. And then z squared is a pair on its own, so I'm going to put z outside. So I will have 9xz square root of 5xy. What would happen if now I change it to a cube root instead of a square root? Now my index is 3. Before I had an index of 2 and I was looking for pairs of numbers. Now I've changed my index to 3, so I'm going to look for groups of 3 of those numbers when I'm doing my prime factorization. So let's break down 48. Well, that's 16 times 3. This is 4 times 4. I have to keep going. This is not a square root. This is a cube root. I am no longer looking for pairs. I'm looking for triplets. All right. So I could do a group of 3 2's. That leaves this 3 and that 2 left over. So this is going to be represented as a single 2 outside of my radical to show that I had one group of 2's and there was 3 of them to take care of this index. You have to make sure if your index is anything other than 2 that you write that inside or in your inside of your little house thing in your radical. And then inside I've got 3 times 2. So this is 2 times the cube root of 6. All right. There is a 2 already on the outside. I'm not going to forget like I did before. So 25 is 10, or excuse me, 250 is 25 times 10. This is 2 times 5, and this is 5 times 5. One group of 5's and a 2 left over. So I have my 2 that was already there multiplied by 5 times the cube root of 2. So this will be 10 times the cube root of 2. All right, I'm going to let you pause. Go give these a try. Then unpause and check your answers. So 16 is 2 times 8, which is 2 times 4, which is 2 times 2. So I'm going to get rid of the ones I've already broken down. There is my triple of 2's with 1 left over. So one of those 2's is going to go on the outside and represent this triple that I have to suffice this index. This leftover 2 has gone inside, and I'm going to show it's a cube root. Now I've got x to the 5th, 4, 5, and I'm looking for groups of 3, not groups of 2. So I have 1 triple of x's, so this represents x cubed. The cube root of x cubed is x, so that's going to go outside. Now I have 2 that are left over that have not completed that triplet, so x squared has to go inside. Y to the 6th, there's one group. There's 2 groups. 6 is evenly divisible by 3, so I can split them into even groups of 3. It's going to be y squared because there are 2 groups of these triplet y's. I'm going to rewrite this just because it's a mess and you can't really see. 2xy squared times the cube root of 2x squared. And last but not least, 56 is 7 times 8. And again, there's a 3 out there. I'm not going to forget, like I did before. This is 2 times 4, which is 2 times 2. 8's gone. 4's gone. I got a triplet of 2's. So that's going to go outside to show that I've met that requirement for taking the cube root. 7 is inside because it didn't have any pairs. This x doesn't even have enough to make it outside because it's only 1. That's got to go back in. Y squared doesn't have enough to make it out because it's only 2, so that's going back in. And z, there are exactly 3 z's, so that creates 1 pair of z that goes outside. And that's the end.